The universe is expanding. This is not a theoretical assumption, but an observationally confirmed property of space-time. In the early 20th century, astronomers discovered that distant galaxies are receding from us, and that their recession velocity increases with distance. This relationship is known as Hubble's law, named after content reference OA site 0, index 0. This discovery established that space itself is expanding, not that galaxies are simply moving through a static background. The expansion of the universe is described quantitatively by a parameter known as the Hubble constant. This value represents the rate at which the universe expands at the present time. It is typically expressed in units of kilometers per second per megaparsec. This means that for every megaparsec of distance, galaxies appear to move away faster by a fixed amount. At first, this concept appears straightforward. However, modern observations have revealed a serious inconsistency. Different measurement techniques produce different values for the Hubble constant. The discrepancy between these measurements is now statistically significant. This problem is known as the Hubble tension. There are two primary methods used to determine the expansion rate of the universe. The first method relies on observations of the early universe. This approach uses the cosmic microwave background, which is the relic radiation from the early universe, approximately 380,000 years after the Big Bang. This radiation encodes information about the initial conditions of the universe and its subsequent evolution. Precise measurements of the cosmic microwave background have been obtained by missions such as Content Reference OSITE 1 Index 1. Using these measurements, cosmologists infer a value of the Hubble constant based on a model of the universe. This method yields a value of approximately 67 kilometers per second per megaparsec. The second method relies on observations of the local universe. This approach measures distances to nearby galaxies using standard candles. Standard candles are astronomical objects with known intrinsic brightness. By comparing their intrinsic luminosity to their observed brightness, their distance can be determined. One important class of standard candles is Cepheid variable stars. Another key class is Type 1a supernovae. These objects allow astronomers to construct a distance ladder, extending measurements from nearby stars to distant galaxies. Using this method, the expansion rate is directly measured, rather than inferred from a model. This approach yields a higher value of approximately 73 kilometers per second per megaparsec. The difference between these values is not trivial. It exceeds the expected margin of error and persists across independent observations and analysis techniques. This indicates that the discrepancy is unlikely to be due to random statistical fluctuations. If both measurements are correct, then the current cosmological model is incomplete. The standard model of cosmology, known as lambda CDM, assumes that the universe is composed primarily of dark energy, dark matter, and ordinary matter. Dark energy drives the accelerated expansion of the universe. Dark matter provides the gravitational framework for structure formation. This model has been extremely successful in explaining large-scale observations. However, the Hubble tension suggests that there may be missing components or incorrect assumptions. One possibility is that systematic errors exist in one or both measurement methods. Extensive efforts have been made to identify such errors. These include recalibrating distance indicators, refining observational techniques, and reanalyzing data. Despite these efforts, the discrepancy remains. Another possibility is that new physics is required. This possibility has generated significant interest in the scientific community. One proposed explanation involves early dark energy. In this scenario, dark energy had a different behavior in the early universe compared to its current state. This would alter the expansion history and could reconcile the two measurements. Another proposal involves additional relativistic particles in the early universe. These are sometimes referred to as dark radiation. Such particles would contribute to the energy density of the universe and affect the cosmic microwave background. There are also theories that modify gravity itself. General relativity may not fully describe gravitational behavior on cosmological scales. Alternative theories of gravity attempt to account for the discrepancy by changing the relationship between matter and space-time curvature. Other models consider interactions between dark matter and dark energy. If these components interact in non-trivial ways, they could influence the expansion rate. Each of these proposals introduces new parameters or modifies existing ones. However, none has yet provided a definitive solution. The challenge is to find a model that resolves the tension. without contradicting other well-established observations. This is a non-trivial requirement. Cosmology is constrained by multiple independent datasets, including large-scale structure, gravitational lensing, and baryon acoustic oscillations. Any proposed solution must be consistent with all of these observations. Future observations are expected to play a critical role in resolving this issue. New instruments and surveys are being developed to improve measurement precision. These include space-based telescopes and large-scale ground-based observatories. Improved measurements of standard candles, as well as alternative distance indicators, may help reduce uncertainties. There is also interest in using gravitational waves as standard sirens. Gravitational wave events, such as neutron star mergers, provide an independent method for measuring cosmic distances. This approach does not rely on the traditional distance ladder. As more data becomes available, it may provide a crucial test of the current discrepancy. If the Hubble tension persists, it could indicate a fundamental revision of cosmology. Such a revision would have profound implications. It could change our understanding of dark energy, dark matter, or even the nature of space-time itself. The expansion of the universe is one of the most fundamental properties of reality, yet its precise rate remains uncertain. This uncertainty is not due to a lack of data. It arises from a conflict between different high-precision measurements. This makes the Hubble tension one of the most important problems in modern physics. It represents a point where observation and theory no longer fully agree. Such points are often where major scientific breakthroughs occur. The history of science shows that discrepancies between theory and observation often lead to new discoveries. In this sense, the Hubble tension is not merely a problem, it is an opportunity. An opportunity to deepen our understanding of the universe, an opportunity to discover new physics, and potentially an opportunity to redefine the foundations of cosmology.